checking your electrofishing equipment calibration is important for a couple of reasons. One, so you know that your equipment is operating correctly, and two, if you're trying to standardize by voltage or amperage or power, you need to know that the settings that you put on the machine or the meter readings correspond exactly with what is going into the water. So what we are going to do for the next few moments here is to calibrate this machine or check the calibration on this machine. The first thing we got to think about, though, is what are the capacities that we expect. So we'll use that Excel program, Backpack Power, and what we need for Backpack Power are the equipment specifications. This particular one has 200 watt average output, 600 volt, and 10 amp maximums. Then we need the water conductivity and electrode resistance. So for the manufacturer, we have the specifications. We measured water conductivity with our trusty water conductivity meter, and that came out to 330 microsiemens per centimeter ambient water conductivity. So the next thing we need to do is check or measure electrode resistance in this particular situation. Now you can do this type of equipment calibration check in the lab or out in the field. In here, we're going to have pretty high resistance because of the small volume of water. So we turn the unit on, we take a reading with our multimeter or oscilloscope, and we get volts and amps and use Ohm's law. That'll give us total electrode resistance. And in this case, we dialed in 100 volts, 102 volts is what we got out, and the amperage was 0.59 amps. So that gave us a electrode resistance of 172. The water conductivity is 330, so at 100 microsiemens, the electrode resistance is 570. So that's the information. We put in the Excel program, Backpack Power. And the reason we do that is to see what the capacities are that we expect this unit to put out. So what are the output capacities? So we know we have some basis for assessing this equipment. The next calibration check we'll make is on the voltage setting. So we'll look at the voltage setting is what we dial in, what we get out, and the voltmeter here is what is displayed, actually what we're getting out. Now you'll use two different pieces of equipment for that, a scope meter and a multimeter. Now we're using pulse direct current, so a scope meter is very good for measuring pulse direct current. Multimeters are oftentimes not suited for pulse direct current measurements, but there are a few on the market that do measure peak voltage on pulse direct current. So that we have one of those meters here. So we'll go first, we'll measure some with the scope meter, and then we'll do the rest of the measurements with the multimeter. So I've got 50 volts set on here. So we're going to watch 50 volts. We're going to see what we get on the screen, and then we'll see what the actual is with the lie detector here. So I'm going to go ahead and turn it on, fire it up. And we have 52 volts showing, 51, 52 volts showing on the voltmeter, and then we have I froze the display here on the multimeter. Now this is a pulse direct current waveform, as you know. Each one of these divisions vertically is set at 50 volts per division. So this is the zero line, it's 50 volts, 100 volts, 150, 200, like that. The divisions horizontally are 5 milliseconds per division. So what we have here, we can see that the waveform is pretty much at 50 volts, which is what we had dialed in and what the voltmeter said. So one way to check that is by something called cursors, and we can take and move these cursors to anywhere on the waveform we want. There's one cursor that's actually on the 0 line. I'll move it down. It's on the 0 line. It was on the 0 line. Now I'll move it up to be exactly on the 0 line. And then I'm going to move this top cursor down to where it's at the top of the waveform, because we're interested in peak, because these are peak reading. And that pretty much does it, and it says 50 volts. So we dialed in 50 volts. The voltmeter said 50, 52, 51 volts. And then the scope meter gave us that, yes, that's true, it was 50 volts. So that's a check. That's a good reading. So we'll go again now to 100 volts. Take the hold off the oscilloscope and take another set of readings. So we have 100 set, 102 volts by the voltmeter, and we'll freeze the display on the scope meter. And again, this is the 0 line, and it's 50 volts per division, so we can look at that and see that the output waveform is pretty close to 100 volts. We'll do the cursors one more time here, and so about, again, nearly 100 volts. So that's what we put on. There's a couple other things that the scope meter does, a couple other measures we have up here. And when I turn the cursors off, we see that we have a reading for duty cycle, 23.4%, and we have a hertz reading, a frequency reading of 59.24. So we look at the waveform that we set in again. We put in a frequency, a rate of 60 hertz or 60 pulses per second. The waveform actually came out at 59, a little over 59, so that's a good match. And we had a 24% duty selected, and we see that the duty measured was 23.4%. So a very good correspondence there. So now what I'm going to do is I'm going to change out the multimeter for the oscilloscope or scope meter, and then progress on for a few more voltage readings, so we can use that, and you can see how that piece of equipment works. All right, now I'm switching out the multimeter for the scope meter here, and so we have the black lead coming from the cathode, the rat tail electrode, and we put that in the COM port. Then we take the red lead. The red lead is attached, the other end is attached to the ring anode, and we put that in the voltage port here because we are going to be measuring voltage, and so we're hooked up. And now we're going to turn the multimeter on so it'll measure peak voltage. We need to turn it to DC volts there, DC volts, because we're doing pulse direct current. We want to set the range to where it'll take in the voltage that we're dealing with, hitting the range button, and we want to have it measure peak volts. And on this particular unit, I have to hit a min-max button and this button, and it will then read peak volts. So let's turn the voltage up now to 200. Apply the voltage. The multimeter, the voltmeter is reading 201 volts. The multimeter, 207 volts. Good agreement again. We'll up it to 250. 250 volts. Apply. Voltmeter says 251 volts applied. Multimeter 257, great agreement. Keep going. 300 volts. Now you can do 25 volts, 10 volt increments, 5 volt increments, whatever your machine will allow you to do. Okay, again, we're at 300, so I think we're good there yet. 299 volts on the voltmeter, 306 volts on the multimeter. So I'm going to make a switch there, go to 350. $350 on the voltmeter, about 358 on the multimeter, 400. $398, 407. Good agreement. Now we're going to go to 450. And now we see we're not getting what we had dialed in. We dialed in 450. We're only getting 414. And then, she cut off, so we had an overload there. But you can see we're getting to the limitations of the machine. So again, we dialed in 450. We only got about 419 volts, and our multimeter said it was 430. So there was some disagreement there in these readings. And then it shut off. So we're at the capacity limit of the machine. Let's take a look at the waveform, because we had a bit of a discrepancy between the voltmeter reading and the multimeter reading. So let's put the scope meter back on, take a look at that waveform for a second. So on that last calibration check at 450 volts, the unit could not put out anywhere near 450 volts, so we're reaching the output capacity of the machine. We'll take a look at the XL tool backpack power here in a minute to see why that was. But immediately we had somewhat of a discrepancy between the voltmeter reading and the multimeter reading on peak output voltage. And so what I've done is I've replaced the multimeter with the scope meter, and we're actually going to look at the waveform. So we're going to apply 450 volts again, or try to catch the waveform and see exactly why there might have been a discrepancy between the voltmeter reading and the multimeter reading. So we've captured the pulse DC waveform at the 450 volt setting. The scale is set at 100 volts per division vertically. So this is a zero line, 100, 200, 300, 400. 450 is what we dialed in. As you can see, the top of the waveform did not get to the 450 mark, but it just exceeded, at the very tip, just exceeded the 400 mark. So let's take a look at this, and we'll put our cursors back on. And here are our vertical cursors. If we go to the very tip of the waveform, maybe right there or possibly there, we see the reading of 415 volts. This corresponded fairly close to the multimeter reading. Now, if we look at the width of the pulse, it's basically 4 milliseconds across, but if we use our cursors, horizontal cursors, this is the point from here to there is the point that the pulse width is 1 millisecond wide. And we use that kind of as a rule of thumb that the fish need at least 1 millisecond of pulse width to react to. So if we bring our vertical cursors then down to where the pulse width is about 1 millisecond wide, we're looking at 395 volts peak, maybe 400 volts peak. And that corresponded closely to the voltmeter reading on the unit. So the voltmeter on the unit seems to be reading at 1 millisecond width, the peak at 1 millisecond width, whereas the peak reading multimeter was reading at about the very peak of the waveform. So this is again why you want a scope meter if possible, because at high loading the square wave do tend to deteriorate where they get a spike or they get a slanted top, and that's what we're seeing here in this instance, and the reason for the discrepancies. Okay, we just saw that at a setting of 450 volts we couldn't get that output at a water conductivity of about 330, and Backpack with Power Excel tool told us that that's what we should expect. So what we've done is changed the water conductivity by adding some distilled water and brought the water conductivity down in our test tank to about 145 microsiemens per centimeter. So the Excel program tells us that we should be able to get at least 500 or so volts out of our backpack unit and that kind of conductivity. We recalculated the electrode resistance, and the electrode resistance is about 519 now. So that's the kind of information we put into Excel with Power, or into the Backpack Power program. So anyway, we'll continue this voltage calibration from 450 on up, see where we get. I'm going to turn the dial on the multimeter, get to DC voltage, get the range about 600 volts here, and then tell it to read peak voltage. Got the dial set at 450. Now at a new water conductivity of 145, we'll go ahead and fire it up. And we have a voltage reading now, a peak voltage reading of 451. So 450 set, 451, good correspondence, and on the multimeter, 460. So pretty close agreement. We'll change now to 500 volts. Apply the electricity. Our reading on the voltmeter is about 499. On the multimeter, about 510. Again, good agreement. Now we'll increase to 550 volts. And our multimeter, though, says we're only getting about, or our voltmeter says we're only getting about 496 or so volts. And our multimeter says about 511. So all pretty good agreement. The discrepancy between the voltmeter and the multimeter probably due to that, again, to the loading and the slanted top of the waveform. So the Excel program told us we'd get about 500 volts out as a max, and that's about what we're seeing here. Okay, two other controls that we can check the calibration on this unit is a rate or frequency and duty cycle. So I have the multimeter set here to frequency, and that was basically by setting this dial knob to DC volts and pressing the Hertz button here, and that gave me Hertz. I'll apply electricity. We have a setting of 60 Hertz and 24% duty cycle, so let's see how close we get. So now there's the Hertz, nearly 60, about 59 pulses per second, or Hertz, which corresponds quite nicely with our setting of 60. I'll hit the Hertz duty cycle button once, and that should give us a duty cycle reading, it looks like, of just over 23%, and that corresponds again quite nicely with our 24% duty cycle setting here. So you can go through the frequency range in this particular unit from near 0 up to 1,000. You can go through the duty cycle range in this unit from about 1% to 50% and do exactly like we did for voltage, go just various increments and check to see what the calibration checks out to be. So we've looked at the calibration of voltage, and we've made a measurement comparison for frequency and for duty. Another important characteristic of waveform to look at is current, or amp draw. This particular unit, we don't have a amp setting dial. We only have a voltage setting dial. But we do in this particular unit have a ammeter. So it shares that function with the voltmeter. There it's a voltmeter. I turn the switch over to peak amps, and it's a ammeter. So we'll compare the reading we get from the multimeter with the meter reading on amperage. So typically, at least the old way to do a amp reading was to break in line to the circuit, but now we don't have to do that. We can use what's called a clamp ammeter, where we just clamp it over either the anodic line or the cathodic line. So, and this clamp ammeter doesn't send directly an amp signal, it sends a voltage signal. So we have to make a conversion. We'll get voltage and we have to make a conversion to get to amperage. So here in this case, I'll turn it on and I'll set the scale to 100 millivolts per amp. So we'll get the millivolt reading here. We'll just divide that by 100. That'll give us our amperage. So again, I'll set this unit to DC volts, but actually I'll set it to millivolts because this is going to be a millivolt scale. I want to make sure that we get peak and make the clamp on. We'll compare the ammeter reading with this reading. So here we go, fire in a hole. Okay, so the ammeter on the backpack unit says 1.80 amps, and on the multimeter we have 193.8 millivolts. So now again, this is the millivolt level. To get to amperage, we need to use the scale, which was 100 millivolts per amp. So we divide that 193.8 by 100 millivolts. That gives us an amp reading of 1.9, 1.93, 1.94. That was fairly close to the reading we had, again, on the ammeter. So that is the correspondence. You can go through various amp levels to see if the meter tracks the actual amps that are applied to electrodes by using peak reading multimeter or a scope meter. So then you can run through the voltage measurements just like we did with the backpack unit, starting at low voltages and going up increments and checking the voltage on the voltmeter and comparing that with what you're getting out of on your scope meter or on your multimeter. Then after that, then you want to look at the current and look at the ammeter readings and check that. You don't want to break in line because you'll expose yourself to high voltage, so instead use a clamp-on ammeter. And this, you just clamp this around the conductor and you can use your peak reading multimeter or your oscilloscope, or if you're using AC, a regular multimeter to get current. So where you want to place this is either on the cathode line to the cathode, the hull, or on the anodic line before it splits to go to the booms. If you can't do that, then you can clamp on the clamp-on ammeter on each boom separately, on the line going to each boom separately, and then you add those readings together to get total system current. So once you do that, you can run through the ammeter readings again and check in that, just like we did with the backpack unit.